Today we start our discussion with function generation by analytical method with reference to a 3R1P, that is a slider crank mechanism. As in the case of a 4R linkage, we shall restrict our discussion with to only 3-point synthesis, that is 2 pair of coordinated movement. 3 position synthesis, the reason for this, as usual, is that we can get away with linear equations. If we go for 4 position or higher 5 position synthesis, then we have to handle nonlinear algebraic equation, which is a little cumbersome and beyond the scope of this course. So let me start with a slider crank . O2AB is the slider crank, where 1 is the fixed link, O2A is link number 2, which is the crank, AB, which is link number 3, is the connecting rod, and B, at B I have link number 4, which is the slider. The direction of sliding is horizontal, and through O2 I draw a line parallel to the direction of sliding of the slider, and this we call our x-axis. Perpendicular to that, through this origin O2, we draw our y-axis. The crank angle is measured from the x-axis. The angle that this crank O2A makes with the x-axis we call theta 2, and the position of the slider along the x-axis, that is the x coordinate of the slider, which we write S as the slider position. By 3 position synthesis, we mean that we have to generate 2 pair of coordinated movements of the input link, that is the crank, and the output link, that is the slider. 2, this crank is the input link, and link number 4, the slider, is the output link. So as the crank rotates from position 1 to 2 by an amount theta 2 1 2, the slider should be displaced by a given amount or prescribed amount S12. Similarly, as the crank goes from position 2 to position 3, the slider should move by S23. So these 2 pairs are prescribed, and we have to come out with the kinematic dimensions of this linkage, namely the crank length, that is L2, that is O2A, AB, that is the connecting rod length L3, and the amount of offset, that is the distance of the slider movement line from the x-axis along the vertical direction or y-axis, that is E. That is the amount of offset. So it has 3 link length parameters in this linkage, namely kinematic dimensions are L2, L3, and E. So to generate these 2 pair of prescribed movements, what must be these 3 dimensions? That is what we mean by 3 position synthesis, function generation by a slider crank mechanism. Towards this end, we first obtain the displacement equation as we did in case of 4R linkage. So we write the x coordinate of the point A is L2 cosine theta 2 and y coordinate of the same point A is L2 sin theta 2. The x coordinate of the point B is S, the position of the slider, and y coordinate of the point B is E, the amount of offset. So we can write AB square, which is nothing but L3 squared, where L3 is the connecting rod length. I can write as XA minus XB whole squared plus YA minus YB whole square. Substituting for these coordinates XA, YA and XB, YB in this equation, we get L2 cosine theta 2 minus XB is S whole squared plus YA is L2 sin theta 2 and YB is E. If we expand this, we get L2 squared plus A squared plus E squared minus twice S L2 cosine theta 2 minus twice E L2 sin theta 2. Let me now rearrange the terms of these equations in the following manner. We write S squared is equal to S2 L2 cosine theta 2 plus E L2 sin theta 2 plus L3 squared minus L2 squared minus E squared. Let me now rearrange the terms of this equation in the following manner. We write S squared is equal to twice S L2 cos theta 2 plus twice E L2 sin theta 2 plus L3 squared minus L2 squared minus E squared. So here we write this as d1 S cos theta 2 plus d2 sin theta 2 plus d3. This we replace by d3, d2 is this and d1 is 2L2 with d1 equal to 2L2, d2 equal to 2L2 into E and d3 is L3 squared minus L2 squared minus E squared. For 3-position synthesis, we assume the values of theta 2 and S corresponding to the first accuracy position. So these are assumed. From here I can find the values of theta 2 and S2 corresponding to the second accuracy point as theta 2 1 plus theta 2 1 2. This we have assumed, this is given, so I can find theta 2 2. Similarly, I can find S value of S corresponding to the second configuration or second accuracy point as S1 plus S12. S1 we have assumed and S12 is prescribed, so I can find S2. Exactly the same way I can get the values of theta 2 and S corresponding to the third configuration theta 2 3 as theta 2 2 plus theta 2 3, and S3 is S2 plus S2 3. We have already calculated S2 and we are given S2 3, so I can find S3. Thus, the function generation with 3 accuracy points by the slider crank has boiled down to generation of 3 pairs of coordinated values of theta 2 and S, namely theta 21 S1, which are assumed, theta 22 S2 and theta 23 S3. We can plug in these 3 sets of values in this equation. So we get 3 equations by plugging in the values of theta 2 and S2 in this displacement equation, and we get S1 squared is d1 S1 cosine theta 2 1 plus d2 sine theta 2 1 plus d3. Same way, this equation will be valid for the second configuration S2 and theta 2. So I write d1 S2 cosine theta 2 2 plus d2 sine theta 2 2 plus d3. And for the third position, S3 squared is d1 S3 cosine theta 2 3 plus d2 sine theta 2 3 plus d3. So we get a set of 3 linear equations in 3 unknowns, namely d1, d2 and d3, which can be easily solved. Because we have already obtained theta 21 S1, we plug it in, I get a linear equation in d1, d2, d3. Same way I get 2 more linear equations involving the same set of unknowns, namely d1, d2 and d3. So we can solve for d1, d2, d3, and once I get d1, I get the crank length L2. Once I know d2 and also the crank length L2, I can find the offset E from d2. And once I know both L2 and E from d3, I can obtain L3. As we have mentioned in case of the 4R linkage, we can see that both L2 and E may turn out to be positive or negative. And then if d1, that is L2, d2 in combination with L2, which means L2 and E, these parameters, these crank length and the offset may be positive or negative. And they must be interpreted in the vector sense. That means if E is negative, which means the offset will be below this horizontal line passing through O2. The diagram shows E as positive, and if E turns out to be negative, it will only imply that this line of sliding is below the x-axis. Similarly, if L2 is negative, then theta 2 must be replaced by theta 2 plus pi, as we discussed in case of 4R linkage. Whereas L3, which I will get from this after you know L2 and E, will take the positive root of this L3 squared, we take the positive square root, and L3 is always positive. The thing to note is that if we want to extend this to 4 position synthesis, that is to generate 3 pair of coordinated movements, we have to leave either S1 or theta 2 1, which we assumed one of these two parameters have to be left as an unknown to be determined, and the resulting equations will no longer remain linear in the design variables, and that adds to the difficulty of the solution to this set of nonlinear algebraic equation. Just as in case of 4 bar, we can use this so-called displacement equation to generate instantaneous kinematic relationship by taking derivative. That means if we have to coordinate at a particular position the linear velocity of the slider and the angular velocity of the crank, that can be done by differentiating this equation. Before we finish our discussion on kinematic synthesis by geometric and analytical methods, I would like to point out two things. One is what we have just now discussed, we call a function generation problem. Which is nothing but position coordination. Now, what we mean that if y be a given function of x, where x is the independent variable and y is the dependent variable, if this function has to be generated in a range, say from x initial to x final, xi is x initial, xf is x final, within this domain of the variable x, I have to generate the function y by a mechanism. What it basically means is that the input movement, for example, the movement of the crank delta theta 2 represents the change in the independent variable x, that is delta x. Similarly, the change in the output variable, for example, delta theta 4 in case of a 4R link or delta s in case of a slider crank, these are the change in the output variable. This represents the change in the dependent variable y, that is they represent delta y and this they represent delta x. It is usually we take that they represent this vector in a proportional manner, that is we write say Rx into delta x, where Rx is a constant. Similarly, here we represent the output movement is proportional to the change in the dependent variable, and the proportionality constant is Ry, which is again a constant. So, Rx and Ry, these are constant, and these two constants are called scale factors. In this precision point approach which we are discussing in this entire course, what we mean that I know I cannot generate this function in the entire range. So, we take some accuracy points, and as the first choice I said we should take the Chebyshev's accuracy points, where suppose for 3 accuracy points I should take x1, x2, x3 in this range. I write xj, which will be a minus h cosine 2j minus 1 into pi by 6, and j goes 1, 2 and 3. So, 3 accuracy points in this range is given by this formula, which we then call, we are taking 3 Chebyshev's accuracy points, namely x1, x2 and x3, and correspondingly find what is the values of y, which will be y1, y2 and y3. In this expression, if we remember, a means the midpoint of this range and h is half of the range, So, if we have to generate this function by a mechanism in this range, I calculate A and H, then I calculate x1, x2, x3 by putting j equal to 1, 2 and 3. Once I know x1, x2, x3, from the given relationship, desired relationship, I can find y1, y2, y3, and then we use this to get the input and output variables. How do I get that? That means we assume theta 2 1 and theta 2 2 minus theta 2 1 will be Rx into x2 minus x1. So, the scale factors are again assumed. These Rx and Ry constant, the scale factors, these are assumed. Once the scale factors are assumed, theta 2 1 is assumed. I have already got x1, x2. Sorry, I should write rather x1, x2. The second accuracy point x2, j equal to 2, and the first accuracy point j equal to 1, x1. So, x2 and x1 are known, Rx we have assumed, theta 2 1 we have assumed, so I can get theta 2 2. Similarly, for theta 4, I write theta 4 2 minus theta 4 1 is Ry into y2 minus y1. So, this is what we mean by function generation by a mechanism, that the independent variable, change in the independent variable is represented by the input movement, change in the dependent variable is represented by the output movement. Mechanism only takes care of this movement, not their exact values. So, there we assume theta 2 1 and theta 4 1, and this movement is controlled by the mechanism. Rx and Ry we assume suitably such that the range of the movement is within the desired range. Now, we discuss a very important point so far as this kinematic synthesis of linkages are concerned, which will tell us that we must always verify after the design has been attained whether the linkage is performing satisfactorily, because whether we solve by geometric method or by analytical method, we can never ensure that a mechanism performs satisfactorily because of two reasons. One is known as branch defect. A mechanism synthesized by either geometric method or analytical method may undergo what is known as branch defect. Let me explain what is branch defect. If we remember that if a 4R linkage is Grashof type, then there are two distinct branches. If this is the input angle theta 2 and this is the output angle say theta 4. Suppose we are talking of a crank rocker, which obviously means it must be Grashof type. If it is a crank rocker, then we know the input angle rotates completely, that is from 0 to 2 pi, whereas the output link rocker only rocks between 0 and pi or between pi and 2 pi. And there are two distinct branches in the sense that for one mode of assembly, maybe this is the relationship between theta 2 and theta 4, whereas for other mode of assembly, this will be the relationship between theta 4 and theta 2. Now, when we do 3 position synthesis, like suppose the desired values are theta 2 1, theta 4 1, theta 2 2, theta 4 2, and theta 2 3 and theta 4 3. And suppose these 3 sets are like one point here, this is theta 2 1, this is theta 4 1, this is the second point, that means this is theta 2 2 and this is theta 4 2, and this is the third point, this is theta 2 3 and this is theta 4 3. what we realize, it is with the same link lengths all these 3 points are satisfied, but all the 3 points are not satisfied by the same mode of assembly. So, our method, whether geometric method or analytical method, may give us the link lengths L1, L2, L3, L4, which is capable of attaining all these 3 positions, but not by the same mode of assembly. One mode of assembly takes the position 1 and 2, whereas the other mode of assembly takes the third configuration. Then it will be totally useless, because we cannot move from one assembly to the other without dismantling the mechanism. This is called branch defect. There is another defect which also should be checked for after the design is complete, that is called order defect. For example, if we remember that suppose we have a double rocker type mechanism, and I draw the theta 4 versus theta 2 for a non-Grashof double rocker. If we remember that non-Grashof linkage has only single mode of assembly, so there cannot be any branch defect. But suppose this is the relationship between theta 4 and theta 2 for a non-Grashof double rocker, and this entire curve is obtained by the same mode of assembly. But suppose we go for a 4 position synthesis, and the points are like this. This is point 1, this is point 2, this is point 3, and this is point 4. So, we want to attain these 4 combinations of theta 2 and theta 4, 1, 2, 3, 4. But as we see, we will get some link lengths which will satisfy all these 4 configurations, but if we drive the linkage, then there is an order defect. It does not go from position 1 to 2, it goes from position 1 to 3, then 3 to 4, then comes to 2. If we drive the mechanism the other way, then it will go from 1 to 2, then 2 to 4, then 4 to 3. So, these 4 positions 1, 2, 3, 4 are not taken up in the same order as desired. If I rotate it this way, I am getting 1 to 3 to 4, then back to 2, and if I drive it the other way, then it is going from 1 to 2 to 4, then to 3. So, if we want these 4 positions to be taken up sequentially in this order, then this mechanism, though theoretically satisfies the 4 configurations, will not be of any use, because these 4 positions will not be taken up in the proper order. This is what we call order defect. And order defect can happen both in Grashof and non-Grashof type linkage, whereas branch defect can occur only in Grashof linkage, because Grashof linkage 2 branches are totally separate, whether crank rocker, double rocker, or double crank. In all 3 cases, there are 2 distinct branches, and you cannot move from the same mode of assembly from one branch to the other. I will show this with a typical example. Let me now discuss an example to explain this, what we mean by branch defect. We talk of an example with respect to a 4R linkage. Let O2, AB, O4 is a 4R linkage which we want to design such that it satisfies 3 coordinated positions of theta 2 and theta 4, namely theta 2 1 is equal to minus 40 degree. Let me now talk of the synthesis of this 4R linkage with the following specification. We assume theta 2 1 is minus 40 degree and theta 4 1 is minus 68 degree. Then we assume theta 2 1 2 is 26 degree and theta 4 1 2 is 54 degree. And theta 2 2 3 is again 26 degree and theta 4 2 3 is 26 degree. It is clear that we want to solve this problem by analytical method using Freudenstein's equation, because that is why we have assumed theta 2 1 and theta 4 1. For these two prescribed sets, I can find out value of theta 2 corresponding to the second configuration, that is theta 2 2, which is minus 40 plus 26 degree gives me 14 degree, minus 14 degree. And theta 4 2 is minus 68 degree plus 54 degree, that gives me again minus 14 degree. Similarly, theta 2 3 is 26 degree minus 14 degree, that gives me 12 degrees, and theta 4 3 is 26 degree minus 14 degree, that gives me 12 degrees. So the whole problem has boiled down to generation of these three pairs of coordinated values of theta 2 and theta 4, namely 40 degree, minus 40 degree, minus 68 degree, then minus 14 degree, minus 14 degrees, and 12 degrees and 12 degrees. So we write the Freudenstein's equation for this configuration of the 4R linkage with the input link on the left, that is cosine theta 2 minus theta 4 is d1 cosine theta 4 minus d2 cosine theta 2 plus d3, where d1, d2 and d3 are the three design parameters, where d1 is L1 by L2, d2 is L1 by L4, and d3 is L1 squared plus L2 squared minus L3 squared plus L4 squared divided by twice L2 L4. So let me now plug in these three sets of values of theta 2 and theta 4 in this equation. What we get? Cosine minus 40, that is cosine 28 degree, is d1 cosine minus 40, we can write cos 40 minus d2 sorry, this is 68, right, 68 degree, minus d2 cosine theta 2, which is 40 degree, plus d3. Now if I use this set, theta 2 and theta 4 are same, so this is 1, and here we are getting d1 cosine 14 degree minus d2 cosine 14 degree plus d3. And if I use the third set, again theta 2 and theta 4 are same, so cosine 0 is 1, and I am getting d1 cosine 12 degree minus d2 cosine 12 degree plus d3. if I subtract these two equations, I get 0 is d1 cosine 14 degree minus cosine 12 degree minus d2 cosine 14 degree minus cosine 12 degree, which clearly tells me d1 is same as d2. Now, d1 is same as d2, then from here I am getting d3, any of these equations I am getting d3 is equal to 1. And what is the value of d1 I can get by substituting d3 equal to 1 and d1 equal to d2 in these equations. The thing to note is, if d1 is equal to d2, that clearly tells me L2 is same as L4. That means the crank length and the follower length are equal, and d3 is 1 and L2 equal to L4. So, let me put it here. If I put L2 equal to L4, then and d3 is 1, that is 1 equal to L1 squared minus L3 squared divided by 2 L4 squared plus L2 squared plus L4 squared is 2 L4 squared, and this is 2 L4 squared. So, that is 1, which clearly tells me 1 cancels, L1 is equal to L3. So, the final mechanism has come out to be that the fixed length is equal to the coupler length and the crank length is equal to the follower length. That means two opposite link lengths are equal, which means it can be either a parallelogram or an anti-parallelogram. It is obvious to note that 14 degree for both theta 2 and theta 4 can be taken up by a parallelogram configuration. Similarly, this minus 14 degree plus 12 degree will be also taken up by the parallelogram configuration, whereas minus 68 degree and minus 40 degree cannot be taken up by the parallelogram configuration, and we will see by the model that it will be taken up by the anti-parallelogram configuration, which means we have to go from the parallelogram to the anti-parallelogram branch to obtain all the three configurations. This we will now demonstrate with respect to a model. Let us now look at the model which has been designed with the values that we have just obtained. We said theta 2 1 is minus 40 degree, theta 4 1 is minus 68 degree, theta 2 1 2 is 26 degree, theta 4 1 2 is 54 degree, theta 2 2 3 is 26 degree, and theta 4 2 3 is again 26 degree. We have already seen L2 comes out to be equal to L4 and L1 comes out to be equal to L3. We take L1 equal to 5.1 centimeter in this model, and we have seen that D1 or D2, which we found to be equal, could have been solved by using the first equation, and if you solve that equation, it turns out to be about 0.3. This is the model that we have got. This L1 is 5.1 centimeter and L1 is equal to the coupler length L3, and L2 is also equal to the follower length L4. This is the first configuration where theta 2 1, that is angle that this link makes with O2O4, that is minus 40 degree, whereas the angle that this follower makes with the same line O2O4 is minus 68 degree. So, this configuration is taken up by this anti-parallelogram assembly, whereas the second position, which is minus 14 degree for both, is these two configurations. This link should come here, this link should go there. These are the third configuration, both at 12 degree. This is where this link should come and this is where this link should come. But if we drive this link, as we see, this second position is not being taken because it is still in the anti-parallelogram assembly. If we now change it to the parallelogram assembly, then we see the second configuration is satisfied by the mechanism. Same way, if we go to the third configuration, it is only the parallelogram configuration that will take the third configuration, but if it gets into anti-parallelogram configuration, then the first configuration is not satisfied for obvious reasons, because theta 2 and theta 4 are not equal. In this case, we have a transition linkage because L1 plus L2 is L3 plus L4. That sum of these two link lengths is same as the sum of these two link lengths. So we can go from this uncertain configuration either to parallelogram configuration or to anti-parallelogram configuration. But as a mechanism, this will be useless because the switchover cannot take place as soon as it becomes a non-transitory Grashof linkage, and various configurations may be taken up by the different modes of assembly. That has to be checked after we get the design parameters, whether by graphical method or by analytical method. Let me now discuss the same problem if we solve by graphical method. What kind of problem may arise? We talk of this theta 2 1 2 26 degree as before, theta 4 1 2 54 degree as we have considered in the analytical method. Same values of theta 2 2 3 26 degree and theta 4 2 3 is again 26 degree. Because we are solving it by graphical method, we need to assume L2 and theta 2 1 or L4 and theta 4 1. We are solving it by assuming this value of L2 6.4 centimeter and theta 2 1 is minus 40 degree as we have assumed in the Freudenstein's method also. This is what we assume in the graphical method, and we do not assume the value of theta 4 1. If we solve this problem by the graphical method, the solution that we get, we make a model out of it, and I will show you that model and see what kind of problem we face in this graphical solution. This is the model that we get for the solution to this problem by graphical method. This is O2, this is O4. This is minus 48 degree and this is whatever O4 makes. We have got L2 as 6.4 centimeter and these are the other link lengths. This is the mechanism at the first configuration, satisfying. Now, if we move this linkage, these are the desired second configuration which is being taken up by this linkage. These are the third desired configuration, but as we see, if we drive this linkage, when this link is occupying the third configuration, the red link is not occupying the desired third configuration. But if we continue to drive, while returning, it is taken up the desired configuration. This link is along this line and this link is along this line. Now, here again we see that when this link is along this line, the red link which is supposed to be along this line is not taking up the desired configuration. Same is true here, the first configuration, this link is along this line, but the red link is not along this line. But if we drive then during return it is taking up the desired configuration 1 and 2. So, what we see, there is a non-monotonic movement. These positions 1, 2 and 3 are not taking up in the serial order. If we take up 1 and 2, then 3 is taking up during the return stroke, and if we take up the third configuration, then in the same stroke 2 and 1 are not being taken up, 1 and 2 are being taken up during the return stroke. This is not a branch defect, but this is some kind of a non-monotonic movement. That brings us to the end of the discussion so far as kinematic synthesis of planar linkages are concerned. We have discussed in great detail the graphical methods, which also gives you a feel of the movement of the mechanism. Then we discussed in short the analytical method only with respect to function generation problem. At the end, I have drawn your attention to the fact that whether we solve a problem by graphical method or analytical method, the design mechanism should always be checked for satisfactory performance, because there is always a chance of having either a branch defect or an order defect in the design mechanism which we have explained just now.